These massive plumes are composed almost entirely of harmless water vapor. While they look like exhaust, they are a byproduct of a very different process. Actual smokestacks are the tall, thin pipes designed to push combustion gases high into the atmosphere. These wide, curved structures serve an entirely different purpose. Nuclear plants don't burn fuel to create electricity, so they have no combustion gases to disperse. Instead, their towers are dedicated solely to managing heat. By mixing warm, saturated air with the cooler atmosphere outside, these iconic structures effectively act as giant industrial-scale cloud machines. Thermal power generation relies on boiling water to create steam. That steam expands and forces its way through massive turbine blades, providing the mechanical force to spin a generator. Once that steam passes through the turbine, it must be condensed back into liquid water to restart the cycle. Venting the steam into the sky is an expensive waste of feed water that has been chemically treated to prevent mineral buildup and corrosion. While some plants use nearby lakes to absorb this excess heat, that isn't a viable option for every location. Building massive mechanical refrigeration units could solve the problem, but the electricity required to run them would consume much of the power the plant just generated. The engineering challenge is clear. The plant must cool tens of thousands of cubic meters of boiling water every hour without wasting its own electricity. Efficiency starts by using the ambient air. Hot water is pumped to the top of the tower and dripped over fill, layers of textured plastic breaking the liquid to maximize their surface area. As dry air passes the droplets, some of the water evaporates. This process absorbs latent heat from the remaining liquid, allowing the water to cool even below the temperature of the outside air. Evaporation at this scale requires a massive, continuous vertical airflow. Usually, moving this much air would require the very fans engineers are trying to avoid. This is where a specific property of air provides a solution. Water molecules weigh less than nitrogen and oxygen. As water evaporates, the humid air becomes less dense and more buoyant than the dry air. This buoyancy creates a powerful, natural updraft. As the light, humid air rises, it creates a vacuum at the bottom of the tower that draws in a fresh supply of drier air. The result is a self-sustaining buoyancy engine. It pulls hurricane-force winds through the falling water using absolutely zero moving parts. Generating enough of this natural draft requires a chimney of immense scale, often over 650 feet tall and 400 feet wide. A straight cylinder is structurally weak at this scale. Like a soda can, its weight would cause it to buckle, and its immense surface area is vulnerable to wind shear. The solution is a double-curved hyperboloid, channeling these forces safely into the ground. This is the Pringle factor. A flat sheet is flimsy, but opposing curves provide stiffness, cutting structural stresses in half. This curvature provides the structural integrity needed to maintain such a massive hollow shell and keep it upright without it collapsing under its own weight. Because this system relies entirely on the local weather to drive its internal engine, it faces a major geographic limitation. In certain hot climates, the air state stalls out on the psychrometric chart. As the air moves through the tower, it loses its buoyancy and stops rising before it can reach the top. When the draft chokes, the airflow stops, and the tower fails to provide the necessary cooling for the plant. This makes natural draft towers a calculated gamble. They are typically reserved for long-term nuclear plants, where the 50-year lifespan justifies the massive upfront cost of a structure that provides free cooling. A moment of wonder. This concrete shell is a perfectly tuned instrument of thermodynamics. While much of our industrial world is built on straight lines and motorized force, the cooling tower serves as a reminder that the most efficient machine is often a simple curve